So, dear students, welcome back. The course MTH 802 Fields and Galvez Theory. We have already finished the first unit of this course. Now, in the second unit, our first topic is splitting fields. So, first topic of the second unit that we are going to discuss is splitting fields. Splitting fields. Now, if you remember the previous knowledge, suppose I have a polynomial fx belonging to the ring fx where f is a field, then we can find an extension k of f containing a root say alpha 1 of this polynomial fx. So this means what? This means that x minus alpha 1 is a factor of f of x in kx, or you can say that this polynomial the polynomial fx is x minus alpha 1 f1x, where f1x belonging to kx. Now, since k is a field, by the similar argument as we applied to the polynomial fx to the polynomial f1x, we can find an extension L of k containing a root say alpha 2 of the polynomial f1x. Note that alpha 2 is also a root of f of x. Note that alpha 2 is also a root of f of x in k, and k is also an extension of f, and k is also an extension of f, because any extension of this L is also an extension of f, because any extension of k is also an extension of f. So this means what? Now this means the polynomial f1x is x minus alpha to f2x, where f2x is in Lx. But this also means that f of x is x minus alpha 1, x minus alpha 2, f2 of x. So what I'm doing here is I am actually able to write this polynomial fx as a product of two linear factors times the polynomial f2x, where f2x lies in the extension L of f. Now I can continue the process with f2x and all other factors appearing here, so that until I can get all the factors of this polynomial fx as linear factors. So continuing the process, continuing the process continuing the same process, we can get an extension, say w of f, such that w contains all the roots of w contains all the roots of polynomial fx, and so this polynomial fx is now a product of linear factors x minus alpha 1, x minus alpha 2, dot 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 x minus alpha n, where alpha 1, alpha 2, where alpha I running from 1 to n are roots of fx. So the conclusion of this discussion is that given any polynomial, I can always find an extension of the field over which the polynomial has been taken, such that the polynomial is a product of linear factors. Okay, so this motivates us to define the splitting fields for a polynomial. Splitting fields for a polynomial. So let us give the definition, the formal definition of a splitting field. So definition: now the extension field the extension field the extension field K of a field F is called a splitting field for the polynomial f of x in f of x if f of x, the polynomial f of x, factors completely into linear factors, in kx, and so the second thing is important, and f of x does not factor completely into linear factors over any proper subfield of K containing F. Any proper subfield of K, of F, of K containing F. Containing F. So what does this mean actually? It means that this this K is the smallest extension of F containing all the roots of the polynomial fx. So more precisely, K is the splitting field for a polynomial fx in fx if K is the smallest extension of F containing all the roots of this polynomial, all the roots of the polynomial fx. Okay. Now we will prove later on that such an extension always exists. But before going to proving that result, first we shall discuss some examples. So let us discuss some examples of splitting fields. So examples. So first example. Now take fx equal to x square minus 2 belonging to qx. So the polynomial is taken over the field of rational numbers. Now we are interested in finding the splitting field of this polynomial. So we have to find the smallest extension of Q containing all the roots of this polynomial. Or you can say that the smallest extension of Q such that this polynomial splits completely into linear factors. Now note that this f of x can be written as x plus square root 2 into x minus square root 2, completely into linear factors. And this is actually in this q root 2 of x. Or you can say that, or q root 2 contains all the roots of fx. Now we have to ensure that it is the smallest extension with this property. It is the smallest extension of Q with this property. Now suppose K be any proper subfield proper subfield of Q root 2 containing Q such that the roots of this polynomial plus minus square root 2 belong to K. Now K is an extension of Q and it is a subfield of proper subfield of Q root 2. So note that for any A, B being rational numbers, A plus B root 2. Now A and B, they are in this K, root 2 is in K, so the whole element is in K. And this, say it is alpha. But so alpha is any arbitrary element of Q root 2 because elements of Q root 2, they look like this. So this means what? This means that Q root 2 is contained in K. But K is already chosen as the proper subfield of Q root 2. So this means what? This means K is same as Q root 2. So thus Q root 2 is the splitting field is the splitting field field for the polynomial x square minus 2 over Q. Now take the second example. So second example, so let fx equals x square minus 2 x square minus 3. X square minus 2 into x square minus 3, and again I am taking the polynomial over the field Q, rational numbers. Note that this Q square root 2 square root 3, the field generated over Q by square root 2 square root 3 is the smallest extension of Q containing now if it contains square root 2, it also contains its negative. Okay, and similar is the case with this. So containing plus minus square root 2 plus minus square root 3. So thus it is the splitting field of this polynomial. So thus it is the splitting field for x square minus 2, x square minus 3 over q. Now we can also present few more examples. Suppose the third example, suppose I take, so let fx equals x cube minus 2, again our q. Now what are the roots of this polynomial? So roots of fx are, so one root is the real cube root, but the other are complex roots. So roots are alpha, which is the real cube root of 2. We have beta, which is cube root of 2 into minus 1 plus I, okay, cube root of unity. Cube root of 2 times cube root of unity and its square. And alpha, beta and gamma. Gamma is what? Gamma is cube root of 2 times minus 1 minus I under root 3 by 2. So these are the three roots of this polynomial. Again, I would apply the similar trick as we did in the previous example. So let k equals the field generated by alpha, beta and gamma. Alpha, beta, gamma. So it is the smallest extension of Q containing alpha, beta and gamma. So it would be the splitting field. So K is the splitting field for fx over q. But I want to know the description of this field K. Okay. So note that being a field, it also contains alpha over beta, alpha beta inverse, you can say. And that is going to be what? This is nothing but minus 1 plus I under root 3 by 2. Okay. It belongs to K. But 1 by 2 plus minus 1 plus I square root 3 by 2 is also in K. But what is this? This is nothing but I square root 3. Okay. I square root 3. So is in K. Is in K. So I square root 3 is in K, and this cube root of 2 is also in K. So this means the field generated by I square root 3 and cube root of 2 is a subfield of K. It is contained in. So Q I square root 3 and cube root of 2 is contained in K. What about the reverse inclusion? Reverse inclusion is also clear, but K is clearly contained in Q of I square root 3 cube root 2. So this means the splitting field of this polynomial fx has the splitting field as splitting field splitting field as q I square root 3 cube root of 2. So similarly, we can find the splitting field of other polynomials. So we stop this lecture here. In the next lecture, we shall discuss the existence of the splitting field of a polynomial and the degree of extension of its splitting. If you see these two examples, then what is the degree of extension of this K? Our Q. This is what? This is degree of extension of Q cube root 2 I under root 3 our Q. If you remember, it is 6. It is 6. And 6 is what? 6 is 3 factorial. So later on we will prove that suppose I have a polynomial fx such that degree of extension of degree of fx is n, then if k is the splitting field of this polynomial, splitting field of fx, we shall prove that the degree of extension of k over f is at most n factorial. At most n factorial. Okay, so these are the two results that we are going to prove in the next lecture. So we stop this lecture here.